In this particular situation, an object has been kept on a horizontal surface and it has been imparted an initial velocity v0. So this is the initial velocity imparted to the object. This surface happens to be rough and the coefficient of friction on this surface happens to be mu. So friction force is going to act and friction force is going to try to stop the point of contact over here. So friction force will be acting in the backward direction because this object is not given any angular velocity and hence the point of contact has only one tendency to slide in the forward direction. So friction force will be acting in the backward direction. Till what time will friction force continue to act? Till the time wherein the angular velocity of the object would have become such that the point of contact will have essentially zero velocity. So I'll explain that statement again. Let us understand what friction is exactly doing. So this object has a tendency to move in the forward direction and this tendency is encapsulated because of its translatory motion in this velocity v0. So when this object starts moving forward, this point of contact also starts moving forward. So this point of contact is essentially performing forward skidding or forward slipping. So friction is angry. Friction does not want the point of contact to be skidding in the forward direction because the aim of the life of friction is to have no relative motion between surfaces in contact with each other. So this aim is getting violated, so friction will try to stop the point of contact and hence will act in the negative direction or the reverse direction. When that particular scenario happens, what will essentially happen is that this force of friction will reduce its linear velocity because the force is in the opposite direction compared to velocity. So this linear velocity will be reduced. At the same time, angular velocity will be increased. So this is the angular velocity. So because of friction, this angular velocity will be increased, leading us closer and closer to a situation wherein pure rolling can happen. Recall that pure rolling will happen when V is equal to R omega. Here in this question, initially V is equal to V0 and omega is equal to 0. Because of friction, V is reducing and omega is increasing. So from a situation where V is equal to V0 and omega is equal to 0, friction is trying to propel this system from this particular situation to the situation wherein V is equal to R omega. That is what friction wants, so that it can chill and relax and it does not have to be active. Because when V is equal to R omega, the point of contact is going to be instantaneously stationary and hence friction force will not act anymore. Alright, so this is the initial situation. Alright, and this is the situation that the friction force is aiming for, or this is the final situation, we can say. Alright, this is the initial and this is the final situation. Okay, now let us start the analysis. So the friction force F is here kinetic friction. So we can write down the friction force F to be equal to mu n, which is mu mg. We can write it down. Alright, so the acceleration because of friction force, retardation to be exact, but let us say the acceleration because of friction force is going to be mu g in the backward direction or the direction opposite to the velocity. So the equation for the velocity can be written as V is equal to V0 minus AT, which is mu gt. Alright, so this is a kinematical equation out of the three equations of kinematics for constant acceleration. So V is equal to V0 minus mu gt. Alright, now once this is understood, let us also understand how friction is capable of increasing the angular velocity. Of course, it has to increase angular velocity by providing a torque. Now it is providing a torque which is small f into r. See, friction into perpendicular distance. This torque is being provided by friction. So I can write down the second equation as friction. Let me write it down in white. Alright. So friction into r is going to be equal to I alpha. Friction into r is going to be equal to I alpha. Alright. Now friction is mu mg. So here I can write down mu mg r is equal to I alpha. So from this we get alpha to be equal to the angular acceleration to be equal to mu mg r divided by I. Alright. So now we can write down the equation for omega. Omega happens to be equal to omega naught plus alpha t, and initial angular velocity was 0. Omega naught is equal to 0. This we have verbally stated. Now I am writing it down. So omega is going to be equal to 0 plus alpha t. So that is going to be equal to mu mg r divided by I into t. If we were to find out the time after which pure rolling motion starts, if we were to find out this time, so these are the equations that analyze the situation. Usually in a question, when you have got two equations, they will be giving you two unknowns to find. So it is not necessary that always the time will be asked. Any two unknowns can be asked. Let us say the final velocity could be an unknown, and let us say omega could be an unknown. So any two unknowns could be asked, basically. That is my point. See, the third equation that we have is v is equal to r omega. After pure rolling starts, the third equation that we have is v is equal to r omega. Now using these three equations, let us calculate the time after which pure rolling starts. So if we were to find out the time, then what we would do is we'll put v is equal to r omega, and we'll take the value of v from over here and put it over here, omega from here and put it over here. This is what we'll do. So now v, which is v naught minus mu g t. So this happens to be equal to r omega, which is r times mu mg r t upon I. So isolating all the terms that have t in them, this implies v naught is equal to mu g plus mu g mr square upon I whole into t. Alright, so therefore we have, on doing some mathematical jugglery with this equation, we have I upon I plus mr square into v naught upon mu g is the time. So this is the time after which pure rolling will start. So this mathematics is also obvious. I am taking mu g outside the parentheses, and then I'll be left with I plus mr square in the numerator over here and I in the denominator. When I take it towards the left hand side, I'll get I in the numerator and I plus mr square in the denominator. So that's that. Let us box this equation as a major conclusion of our analysis. This is the time after which pure rolling will start. Now if we were to find out omega and v, then we are simply to plug in this time in this equation and this equation, or if we are finding out omega, then we can simply find out v by the formula v is equal to r omega. Alright, now as far as physics based logical analysis of this question is concerned, there is another method in which we can find out, probably in shorter mathematical analysis, the final velocity and the angular velocity. This new method would be employing the conservation of angular momentum about a certain point or a certain set of points basically. So let me also venture into that method and explain how it works. Now let us analyze any point about the ground. So let us say any point on the ground I am going to take, let us say this is the point P on the ground. Alright. Now about the point P, the initial angular momentum of the object. So angular momentum of an extended object that is performing translational as well as rotational motion is given as L is equal to LCM. LCM is the angular momentum about its own center of mass plus R cross M into VCM. So this is the angular momentum of this extended object about the point P. This is a fairly advanced type of analysis. Alright. So initially there is no angular momentum about the center of mass because this guy is not rotating about its center of mass initially. We again note that omega initial happens to be 0. Now angular momentum about the point P is going to get conserved. Why? Because let us understand all the forces acting on this object. There is this normal reaction which is always and forever pertinently cancelled by mg, and the only other force is friction, and the friction force passes through the point P. So because of that, angular momentum about any point that is lying on this surface in the path of motion of this particular object is going to be conserved. So this happens to be the initial angular momentum. After a while, when this object starts pure rolling, then the angular momentum about point P, so initial angular momentum, let me write down initial angular momentum first, okay? So initial angular momentum is going to be equal to LCM is 0, so R cross MV. So R cross MV will give me, like, this is the position vector R, alright, and cross MV. So I'll have to employ this particular angle. I have to extend this line, let us say further. Let us say I extend this line further and I employ, so I employ this angle, okay, this angle. So for initial angular momentum, I'll have to find out this distance, let's say small r, and then that angle, I have to take the sine of that angle. However, I actually don't need to do that because sine of that angle theta is the same as sine of alpha, because theta plus alpha is 180 degree, and we know that sine of 180 minus theta is sine of theta. So that means sine of alpha and sine of theta are going to be the same values, and small r sine theta is nothing but the perpendicular distance over here. So small r sine theta happens to be this particular perpendicular distance, and that particular perpendicular distance is r, and no matter where the point P is situated, this particular analysis always holds good. So angular momentum initial is always going to be equal to mv naught r, even after taking the cross product. Alright, so it is, that point is important to note. So this is r, this angular momentum is r mv naught. This is the initial angular momentum. The final angular momentum will be a combination of r mv, alright, r mv plus the angular. So this term was not present in the initial angular momentum case, so this term will also come now. So plus I omega. So I omega is I is the moment of inertia about the center of mass, and omega happens to be the angular velocity. So I into omega. Okay, so omega can be written as V divided by R, but I will first write it down as I omega only, and then I will write this down as R and V plus I into V divided by R. So from this particular equation, we get R mv naught to be equal to V into bracket I plus mr square upon R. So if we are to find out the final velocity, it is simply mv naught r square upon I plus mr square. This is the final velocity V. Alright, and if we are to find out omega, it is simply equal to V divided by R, which is mv naught r upon I plus mr square. So thus, via using angular momentum conservation, we can directly, possibly in lesser number of mathematical steps, find out the final velocity in such a situation, because angular momentum is conserved about any point lying on the ground. Alright.